The first of these will be given by Victor Zendejas Lopez from Caltech. He's in mechanical engineering. Dan Myron is his advisor. He did his 2 practicums, actually, at Lawrence Livermore National Laboratory. 3, okay. Okay, 1 now. We're not counting that yet. You got to cross the finish line. Okay, and Victor will be talking about implicit large eddy simulation of Rick-Meshkov and Taylor-Green vortex instabilities. Let's thank Victor. Welcome, Victor.
So essentially today what I'm going to be talking to you all about is capturing turbulence on computers. So the first part of the talk, we're just going to get our bearings, get a basic introduction about what turbulent fluid flow is. And for the second part, I'll show you all some of the numerical test cases that I ran. So what is turbulent fluid flow? There are examples of this everywhere, whether you're talking about the surface of planets, in and on our sun. The interaction between the atmosphere and a wind farm introduces turbulent fluid motion. When you have volcanic eruptions, there's also examples of turbulent fluid flow there. And not only do you have turbulent fluid flow on the scales of planets, but those of you familiar with this golden object called the HOLROM, which is used in inertial confinement fusion, know that this little blob of turbulence started its life in this little tiny. There isn't a well-defined mathematical property of what turbulence is, but there are some physical characteristics. It tends to be multi-scale, 3-dimensional, unsteady, and induces some kind of mixing. So if you're a grad student like me, one of the habits I picked up is I started becoming addicted to coffee. I enjoy creamer with my coffee, but I don't like to wait for the creamer to diffuse into the coffee. So I take a spoon, I mix it, and you get something like this. So believe it or not, when you do this, you're actually doing a physics experiment each and every time, where you're introducing energy in this, let's call it coffee system. And the energy that you're introducing, because coffee and creamer have viscosity, it's going to dissipate that energy. So let's be a little bit more methodical about what I mean. So imagine you're stirring your cup of coffee. What you're doing is you're introducing fluid motion, and you're introducing these wave packets I'm going to call eddies. And it's going to be very important throughout the rest of the talk. I'm going to refer to the length scales that describe these eddies. I'm going to refer to them as length scales, and you can think of them describing the diameter of what these eddies are. So each of these eddies has a different job. So you're injecting energy here at the larger scales. You have these intermediate-sized eddies that are going to cascade that energy down to the smallest eddies, which are then going to dissipate that energy. So let's be even more methodical about what I'm describing. So let's just say you found a way to represent your mixing process. You take a time snapshot, and you found a way to get a discrete data representation. What you can do is you can apply something called discrete Fourier transform, which is just a fancy way of saying you can just apply a linear transformation. You can look at your data through a different lens. That's all I'm doing. What you can compute is something called the kinetic energy as a function of k, which is a wave number. So all you're doing is you're just transforming this data into the frequency domain. So if you plot this on a log-log scale as a function of wave number, the wave number corresponds with your frequency. So I know it's a little confusing at first. All this means is that this is just describing the characteristic scales of each of these eddies. So 1 over L could be eddies that are on the size of the diameter of your cup of coffee. And this 1 over eta corresponds with eddies that are essentially dissipating the energy that you're injecting. So you have the energy containing range. So this is where you stick your spoon in, introduce energy in. You have this inertial range, which is going to introduce this energy cascade. That's what the intermediate-sized eddies are doing. And then you have the dissipation range. This is where all your energy is essentially leaving your system. This minus 5/3, it's not a number that I came up with. There's some beautiful theory that you can do to develop this number. And this number is very important because what it's telling you, it's giving you an indication of the dynamical behavior of your turbulence as far as how it should transfer energy throughout your system. So whenever you look at the surface of turbulence on a planet, your cup of coffee, it doesn't matter. Most of these problems, you'll see some kind of representation like this. It's not always minus 5/3, but it's something very close to this. Okay, so I argue, this is my opinion, that all numerical methods, all these computational fluid dynamic codes that exist, at the end of the day, what we're trying to do is, as faithfully as possible, is capture this process. So now let's talk about how we're actually going to represent this, doing this on a computer. So let's take our governing equations, which I'm not going to bother writing down. And because we're trying to put these equations onto a computer, we need to discretize these equations. So this grid represents that spatial discretization. So remember, you have these small eddies, and what's going to happen is that these small eddies in your system are going to talk to the intermediate size eddies and the larger eddies. They're all going to interact with each other. What direct numerical simulation does is it captures the effects of this process without the assumption of any model. Now, if we start to move on and think about something other than our cup of coffee, we start thinking about real engineering applications, what's going to happen is this inertial range is going to become much wider. What that means is you have a wider range of scales that you have to resolve, and this dissipation range, those scales are going to become smaller. And remember, you still have these large eddies that are in your system, but then now you have all these other eddies sizes that you introduce. But when it comes to real-life engineering applications, a direct numerical simulation is often a bottleneck because the computational cost just starts to skyrocket. So what people have done is they said, okay, at the dissipation range, the scale's there. They don't care about how the energy was introduced into your system. Its job is just to get the energy the heck out of there. So it doesn't matter if you use a fork or a spoon or a hammer to mix your creamer in your coffee. You just want that energy. These scales are just going to dissipate that energy. So what large eddy simulation does is it says, let's just resolve the larger scales explicitly, and the effects of dissipation are captured by a model. So this is a way of saving on computational costs. However, one of the main drawbacks is when we start talking about multi-physics applications, you need to develop a model because different physics are going to interact with these small scales in different ways. And that's actually a very active area of research today. On another similar along the lines, another similar thought is, well, you have your conservation equations, you're putting them on a computer. So this act of discretization, you're introducing an error. And this error can act as a numerical dissipation. So what ILES says is, let's just let the numerical error act as a dissipation for your problem. And one of the pros of this approach is that you don't need additional physics. You don't need additional model for additional physics. So ILES has originated actually in the national labs and has been quite successful as a result. So for the rest of the talk, I'm going to be using ILES, and then I'll give you some more intuition about how it works when I explain the simulations that I'm conducting. But this is just a very high-level overview. There's tons of gory details that I'm glossing over. Okay, now for some test cases. So the code I'm using for my PhD is called Marble. It's a high-order finite element code that was developed at Lawrence Livermore National Lab. It's an AOE code. What that means is it's an arbitrary Lagrangian Eulerian code, which is a mouthful. All that means is that my conservation equations, for those of you who care, I'm solving the Euler equations. I'm solving them on a moving mesh. But because I'm interested in doing these turbulent flow calculations and I have velocity gradients, this can quickly start to kill the quality of my solution over time. So what Marble does is it has this, after the Lagrangian phase, it has this remap phase where after a certain amount of cycles, the solution will check to see how the quality of the mesh is doing, and it'll optimize the mesh and then transfer whatever quantities I'm evolving onto a new mesh. So I think it's best to show you an animation of how this works. So this is a test problem that I cooked up. I call it a shock in the box. It's just two different gases. You're going to see a shock wave hit this interface. But what I want you to pay attention to is what's happening on the right-hand side. So this is the evolution of the mesh. So you may be wondering, why are we bothering using something that looks very complicated, an AOE code? Well, it turns out for some problems that are multi-material, this method introduces a minimal amount of diffusion between different contact surfaces. So here you can see how the mesh is keeping track of not only the shock wave, but the material discontinuities as well. Okay, so the first problem that I implemented into this code is called the Rickmar Meshkov instability. it's a fundamental hydrodynamic instability that exists in nature and engineering, and it's of primary concern actually in inertial confinement fusion. So the way this instability works, it's kind of similar to the video I just showed you actually. You set up this shock in the box experiment where you have two different gases, one that's at a much higher pressure than the other. And because you have two different gases, you have a difference in the densities, which introduces a density. What's going to happen as you let this simulation run is that the density gradient and the pressure gradients are going to talk to each other, and they're going to deposit what we call vorticity along the interface, which is going to destabilize the interface and is going to induce turbulent mixing. So this is called the single reshock case. It's its own subfield of study. I decided to make life a little bit harder for myself, and I decided to study the reshock case, where after the first shock wave hits the interface, a second shock wave traverses back and totally destroys any memory of the initial conditions. And I'll show you how this works. I did a simple grid conversion study for a 3D calculation. I'll show you a 2D animation first. So one of the reasons why we were excited about this problem is because adaptive mesh refinement for this code was a fairly new feature when I implemented this problem. So this is a good candidate for AMR because I have two things that are moving in space. I have a discontinuity, a shock wave, and then I have mixing that's taking place in the material interface that's also moving in space. So here's an animation. So the material colors, so these colors correspond with two different materials. White corresponds with material 1, and black corresponds with material 2. And what you're going to see is that the adaptive mesh refinement in action. So here you see the shock wave just exited the interface. This is destabilizing, it's growing. And you can see the second shock wave, or from the first, is going to come back and just totally destroy any memory of the initial condition. So if I were to ask you, what did this look like at the initial time step, it would be kind of hard to tell. And this is one of the hallmarks of turbulence, is that any memories, when you're doing these simulations, that any memory of the initial conditions should be forgotten. Okay, so now a set of 3D calculations. So here you see three different levels of refinement where I doubled the grid resolution at each time. So to kind of give you an intuition about what implicit large array simulation does, is that because I'm relying on my grid resolution, in a sense, to act as a dissipation scale, as I increase the grid resolution, I'm minimizing dissipation, which means I should see more turbulent structures. And that's exactly what's going to happen. So you're going to see for the level 5 refinement, even now, you can comparing this across here, you can see that there's more structures developing here. And then by the time the second shock wave hits, you see that there's more details as far as the structure and the gradients of the density go. So this is what you're looking at here. Okay. The last test case is the Taylor-Green vortex problem. I call this the hello world of turbulent simulations because the initial conditions are exact to set up. And if you ever pick up a paper that talks about a new numerical algorithm or a code, one of the first test problems they always test is this problem. And the reason why that is because this problem introduces a shearing instability, which induces vortex stretching, and the problem will then transition to turbulence as a result. Right, so I did a basic grid convergence study here. So very similar to the previous simulation, what you're going to see is, so this is the velocity field, so it's set up on a triply periodic cube. So this test case, I doubled the grid resolution with respect to this one. So as a result, you should see more turbulent structures. So this is a decaying problem. So I start off with a certain amount of kinetic energy, and as the problem destabilizes, it's going to transition, and then towards the end is full-blown turbulence. So this problem doesn't occur in nature, but it's a good exercise. It's a good smoke test for numerical codes because capturing this transition is actually a fairly difficult process. Now these eyeballs, so these things that look like eyeballs, so this is something called Q criterion, which I implemented in the code, and it's a way of identifying turbulent structures. So what you're going to see is you start off with these large structures, which are indicative of laminar conditions, and as a problem starts to transition, you get smaller structures, which is telling you that you have more of a turbulent state. So at this point, you don't see very much of the larger structures, and again, comparing the left to the right-hand side, you see that because the dissipation scales here are much smaller, I should see more turbulent structures. So hopefully those of you in the back could kind of tell the difference. Okay, so last thing. So whenever we're doing these turbulent calculations, the videos are nice, but we're often interested in integrated quantities and statistics because this is how we compare and benchmark with other codes. So here, just like I told you in the beginning, we start off with a certain amount of kinetic energy, and the problem starts to decay. Here we're computing something called entropy, which is a measure of our vortical motion. So right around here, so this is the test case I ran where I had the largest grid resolution, so I have the most entropy. And then here it just quickly decays, and this is where we get full-blown turbulence. So there's still a lot left to do with this code. There's a lot of options and opportunities for algorithmic improvements, and as far as how choices in algorithms affect the turbulence that you get is a question that I'm actually trying to answer. I'd like to thank my advisor at Caltech and my collaborators, Rob Reben and Chris Beckwith, who are actually advising me on this project for my PhD. And thank you to the Krell Institute. Not many people know this about me, but I graduated high school with like a 2.12 GPA. Nobody in my family went to college. So navigating undergrad and grad school has been a challenge. But if it wasn't for the folks like at Krell who invested in me, I wouldn't be here giving you this presentation today. So thank you all.